All right, we're back. We're skipping ahead to chapter 9, even though it's the same unit. And we're going to talk about polar and polar coordinate plane and polar coordinates today, and how to graph those polar coordinates. So typically we've been graphing in the rectangular coordinate plane, which is the Cartesian coordinate plane, or the XY coordinate plane. Well, today we're going to talk about the polar coordinate system. So I might have to skip around a bit to catch up with your notes, but the idea is when you are graphing in the polar coordinate plane, you have ordered pairs that are in the form r comma theta, where r is like a radius, if you want to think of it that way. It's the distance from the pole to, how do they describe it here? R is the directed distance from the pole to the point, and theta is the directed angle between. So it has a lot of components that we're familiar with, where it's measuring the angle just like we did in trig, and also in vectors. And then the r, which you probably are associating with the radius from trig, similar idea. But the ordered pairs are going to be written in that way. Now, the way the coordinate plane looks, however, is very, very different. We're supposed to be measuring in a counterclockwise notation, just like we did in trig, and the negative orientation works the same way. But if r is negative, it's going to go the opposite direction along the towards the other direction of the pole. So that gets kind of confusing. This is what the polar coordinate plane looks like. So notice the rings that measure out. Those are measuring the different r's. So this is r1, this is r2, r3, r4. So when I ask you to graph, I'm going to give you this template, and then you're going to plot accordingly. Typically. If we have to graph it by hand, that's kind of annoying because we have to make all these concentric circles, and obviously I can't draw a single circle that looks nice. So let's see what this looks like. This one's already done for you on your notes, but they wanted me to graph the point 3 comma pi over 4. So what you do is you find the angle pi over 4, which is right here, and then you go out positive 3 to the third ring. So 1, 2, 3, boom, right there. That is the ordered pair 3 comma pi over 4 in the polar coordinate plane. Really exciting, right? It says notice that P is on the third circle from the pole, or from the origin, is probably what you're thinking it looks like. This one's a little interesting. Negative 120, so measuring a negative 120 degrees brings you along this line, this terminal side. But because they want negative 2.5 for R, you actually go back the other direction. So you go back 1, 2.5, and you end up right there. Now, there's other ways that you could indicate that ordered pair besides what we just did. You know, we could do the, oh my gosh, I'm like having a brain malfunction today. Co-terminal angle to it, and go positive for the R. But that's a thought for another moment on the notes. All right, so these are already done for you. I'm going to skip ahead because I want to catch up to your notes. I want you to find on your notes, the first question that we're going to do by hand is 3 comma 60 degrees. So right there. Coordinate plane given to you. So 60 degrees would be along this line here. That's the angle. That's the terminal side of the angle. And then the third ring. 1, 2, 3. Boom, right there. I know, like crazy, huh? 4 comma negative 4/3. So you can measure back negative 4/3 pi, or if you don't like that, you could find his coterminal angle by adding 2 pi to it, which is, 6 pi over 3. So this is the same thing as positive 2 pi over 3. So we're along this line, and we're supposed to go to r of 4. So 1, 2, 3, 4. There is that ordered pair. If I remember from you guys working with trig, you didn't really like graphing negative radian angles in particular because it was hard to visualize, so you always found the coterminal. All right, this one, negative 150. Degree measures probably doesn't bother you as much, but if it does, you can find the coterminal by adding 360, and then that is 210 degrees, right? So 210 degrees would be right there. They want R, okay, so instead of going out this side of our terminal side, because it's negative 2.5, you have to back up. Oh gosh. Over here. 1, 2.5. That is the ordered pair that they want. How irritating, right? feel like I just messed up something, though. We're good. I don't know. You know, on my page, this might be a different question. Oh no, that's what the question says. We're good, we're good. Alright, moving along. So we referred earlier about how the same point can be named multiple different ways. So that's kind of irritating because you can do all the coterminal business where you add and subtract 360 or 2 pi if it's radians. But that negative r value goes the other direction along the terminal side. So you can also consider that to be an issue. I think it shows up right here. So in addition to not just the coterminal issue, if you negate the r, then you're supposed to add or subtract 180 or pi, because that'll take you to the other side of that terminal ray, the other side of the line, I guess, if you want to call it that way. So measuring clockwise versus counterclockwise, there's just so many ways that we can mess around with this. This one is not in your notes, but I think it's a good one for us to look at. Before I say that, let me make sure that's true. I think it is. Yeah, this one's not in your notes, but that's okay. We can still do this. This is the ordered pair 4, 135. So find 4 different ordered pairs that give you that same point. It's kind of overkill, I think, but whatever. We could do a negative angle, where that would be, let's see, negative 225. So you could do 4, negative 225. You could go to the other side, which is right here, right? So what if we called that negative 45 degrees, but then we backed up 4 units on the r? That would be the same. This angle down here is also 315. And then just 4 units. Oh, negative 4 units, excuse me. Oh gosh. You could just add like complete rotations if you felt like it. So adding a full rotation, let's see, 360 plus 135 would be 495. Oh, but it does say between 360. Never mind, that one doesn't work. Back up, back up. They want me to go radians because they said 360. So who did I forget? Whatever. I'm moving on, guys. It's not worth our time. So here it says find 3 additional pairs of polar coordinates. So this is on your notes. I think it would help us if we kind of had it graphed out, or at least sketched. And you know what my sketches usually look like. They're not great, but that's okay. So I'm going to pretend that I know where 240 is, which I totally do. It's right here. But then remember how we have these weird circles in polars? So it's like 1, 2, 3, 4, 5. Wow. Okay. Anywho, it says that we can go degrees or radians, kind of, sort of, but they want me to stop at pi, so keep that in mind. So another way that I could write this ordered pair, oh boy, that's so bad. If I extend this away, if I keep going along, I don't know if this is my day, guys. Alright, this is a 30-degree angle here, which means this is a 30-degree angle, so this is a 60-degree angle, right? So if I go 60 degrees, and then I back up 5 for r, that would be one equivalent polar coordinate. Oh my gosh, big golly. Alright, what if we backed up 90 plus 30 would be 120 degrees. So negative 120 degrees on the 5th circle. Alright, for the sake of my brain, I'm going to stop coming up with ordered pairs, but you get the idea. We can go radians pretty easily there. We can convert to radians. I'm not going to bother right now. This one is in radians, so remember, you might want to stick around with radians, but if you want to convert this to degrees, that's fine too. It doesn't really say. I think their intention is that if they give the original angle in radians, they want you to stay with radians, but whatever. Alright, pi over 6 is right there. So if I think about this guy, this is pi over 6. This would be 7 pi over 6. Okay, so keep that in mind. But we're on the 2nd circle. Totally nailed it. Okay. So that ordered pair, also known as, what if we went negative 7 pi over 6, but then we backed up to the second circle. That would work. What if we went negative, oh boy, let's see, it would be 11 pi over 6. And then we'd be on the second ring. Yeah, that would work. Okay. There's many others to find, guys. I'm a little short on time here, so I'm going to keep going. All right, so we're on worksheet 4B now. Good news is they gave me a lot of coordinate planes to work with, so thank goodness. But we're going to start graphing polar equations. Kind of, but real basic ones. Right here it says, for example, 2 times sine theta is a polar equation. The polar graph is a set of all points that satisfy r comma theta. So, there's real basic equations in the Cartesian coordinate plane, like vertical and horizontal lines. Well, similarly, there's real basic equations in polars, and that's what we're going to start with today. So graphing r equals a constant or theta equals a constant gives us some very boring graphs. So I'm going to show you what those look like next. The idea is if you are graphing r equals some sort of a constant, essentially what you're graphing is one of those rings, one of those circles. Wow. And then if you graph theta equals some sort of a constant, so you're graphing some angle, you're basically graphing a line that's along that terminal side, but in both directions, the positive and the negative part of the r. So that's what we're going to look for in these real basic graphs. They went ahead and used their calculator by changing it to polar equations, polar mode, and they graphed r equals 2. And then what do you know? It gave you a circle with the radius of 2, or the second ring of the polar equation. But your calculator doesn't show all this like polar grid, so they're a little easier just to graph by hand in these simple ones. So r equals 2 would be all those guys. A circle, radius 2. Boom, centered at the pole. Now pi over 6, that would be the line or the ray that terminates at pi over 6, but in both directions. So you're going to see this line right here is what the graph looks like. So for r equals 3, oh gosh, I just promised you I wouldn't make you graph things by hand, didn't I? All right, so here's our pole, P, and then the third. I gave up. Okay, 2 pi over 3. Man, I thought I was doing good for a minute. I did not. 2 pi over 3 would be, let's see, that would be over here, wouldn't it? But remember, it's got to go both directions, so look something like that. I will be giving you polar coordinate paper or some sort of a grid to graph on. So r equals 3 is graphed for you here. This is pretty boring, I know. Negative 60 degrees is graphed for you there. Remember, both directions along the ray going in both directions, so it creates a line. So here's on your notes, I think they want me to practice. Thank goodness they gave me something to work with. All right, r is 4, so I go 1, 2, 3, 4. I'm supposed to be... Oh, okay. You know, I quit. All right, 3 pi over 4 is... where are you at? Right here. Right? Yeah, this is 3 pi over 4. So this... Wow. Can't draw a line either. It's going to be a rough day. There we go. And then negative 300. Land here. But remember, going in both directions, so... Oh, man. Okay. Alright. It's supposed to be here. You know what I've learned? That I can't draw still. Nothing new. Alright, guys. There's a fun landscaping question coming up next. This one's kind of cool, and I think there's a homework assignment that's like this. So, the landscapers, let's see, they designed a new building for a retirement community. The design calls for a bench ordered pair at negative 460. So 60 degrees, but then going back 4 circles. So let's see, right here. 1, 2, 3, 4. So here's the bench, I think. And then a pond is at 105. So 105 would be like right here, and then 1 out. So like right here. Okay. What do they want? The distance between the pond and the bench. Okay. Yikes. This is the center, right? And everything kind of revolves around the pole there. Well, I have a really disgusting triangle that I just drew, and I did a terrible job. What's new? Looks something kind of like that. And I know, because of the R, or the rings, that this side here from the origin, that was 4 out, so this is a 4. Come on, buddy. You know you want to work today, pen. Or not. And then this was 1 ring, so that's a 1. And I need to know this. Now, this is not a right triangle, so I'm wondering if we could figure out this angle here. And I'm pretty sure we could, guys, because this is the angle 240, this is the angle 105. So that included angle is just the difference between those two. So, real quick, I'm going to subtract 240 minus 105 and get, right. So, 135. Hope I did that right. Yeah, 135. Okay. And now we're going to set up law of cosines, where x is going to be the square root of 4 squared plus 1 squared minus 2 times 4 times 1 times the cosine of 135. Now, I think I already typed this in, or someone did on their calculator, so I'm just going to steal that answer. And it comes out to 4.75 feet. I think that's all we had to do. That was a pretty nice question. If you look down your notes, I think they're on your notes, they give you this formula. And pretty sure that's what we just did, right? This is just the law of cosines that we just used for a side angle side, finding the side opposite of the angle that's given. So there's a big note here from Mrs. Hoffmeyer that she doesn't really use this formula because it's just law of cosines. So same for me. Like, I'm really good at law of cosines, so I don't need to think about how this applies to polar coordinates because it's pretty easy to look at, especially when you have a graph. But if you love this formula, you go right ahead and use it. All right, good news. That ends our lesson on the introduction to polar coordinates and graphing polar coordinates in a polar coordinate plane. You probably have a pretty hefty book assignment, so please practice. This is very unusual and unique, so give it a go.